In the vast and seemingly familiar expanse of space, recent discoveries have revealed something unusual. It's neither a star nor a galaxy, but something much larger. A structure so huge that it shouldn't exist according to our current understanding of the universe. We've long believed that the universe is homogeneous, its matter evenly distributed across the vastness of space. But what if there are anomalies, space giants, that defy this principle? Here in this vast ocean of space, we've discovered not just a cluster of distant galaxies, but a giant ring, a collection of cosmic formation stretching over 3.3 billion light-years. How could such a massive structure exist? What forces set it in motion? And what does its presence mean for our understanding of the cosmos? Today we dive into a story of cosmic discovery. This journey begins with a chance discovery by a team of astronomers and leads to a question that shakes the foundation of modern cosmology. Welcome to the enigma of the huge ring of galaxies. Giant Arc unexpectedly stands out among other celestial structures in the universe. This colossal structure, spanning 3.3 billion light-years, was first spotted by the keen eyes of PhD student Alexia Lopez and her team in June of 2021. Their discovery was not just an astronomical stroke of luck, but a groundbreaking moment in space exploration. The Giant Arc is made up of galaxies, galaxy clusters, and gas and dust. Imagine a structure so huge that it could encompass thousands of our galaxies, a cluster of cosmic material that stretches across the sky in an elegant curve. According to the generally accepted cosmological principle, the universe on large scales is homogeneous and isotropic, meaning that wherever you look, the distribution of matter should be roughly the same. However, Giant Arc exceeds the threshold of 1.2 billion light-years, which calls this principle into question. Its size and formation raise profound questions. How did such a massive structure arise? Does its presence mean that our universe is more diverse and complex than our current models suggest? To unlock the secrets of the cosmos, astronomers have developed ingenious methods to detect and study structures that are beyond the reach of traditional telescopes. Central to this quest is the mysterious light of quasars, the brightest and most distant objects in the known universe. Quasars, with their immense brightness, serve as cosmic beacons. Their light, traveling billions of light-years, carries stories about the cosmos. As it passes through the various structures in the cosmos, this light interacts with them, leaving an indelible imprint that astronomers can decipher. One of the key tools in this space detective work is the study of absorption lines, specifically magnesium-2 absorption lines. When the light from a quasar passes through a region of space containing magnesium-2, the matter absorbs certain wavelengths of light. This absorption leaves distinct signatures in the light spectrum that astronomers can analyze. They can reveal the presence of otherwise invisible structures, such as the Giant Arc. These innovative techniques have revolutionized our ability to detect and understand the vast hidden structures of the universe. By analyzing the light from quasars, astronomers can map the distribution of galaxies and intergalactic matter, revealing the tangled web that binds the cosmos together. This method of cosmic observation is akin to using a flashlight to reveal the contours of a dark room. The light of quasars illuminates the grand design of the cosmos, revealing the colossal structures that form the fabric of our universe. Venturing deeper into space, our journey leads us to another startling discovery, the Big Ring. Spanning an astounding 1.3 billion light-years, This enormous structure is a colossal cluster of galaxies and ranks next only to Giant Arc in its defiance of the cosmological principle. Discovered following the Giant Arc in early 2024, the Big Ring represents another monumental find in astronomy. The structure forms a celestial loop of galaxies, gas, and dark matter intertwined in outer space with a circumference of about 4 billion light-years. The immensity of the Big Ring is not just a matter of size. If we could go outside and see it directly, it would take about 15 full moons to cover its diameter. How did such a structure form? What processes could have led to the creation of a ring of galaxies of this scale? These questions pique the curiosity of scientists, forcing us to expand the scope of our understanding of cosmic evolution and structure formation. So let's go take a closer look at the cosmological principle, the fundamental theory in astrophysics that assumes the existence of a universe in which matter is uniformly distributed and all regions look roughly the same. However, as we've mentioned, the existence of such a colossal structure spanning billions of light years disproves this notion, indicating that the universe is far more complex and diverse than we ever imagined. In such a case, it's quite appropriate to ask, how did such huge structures form? And what does their presence tell us about the evolution of the universe? Comparing these structures to others, such as Sloane's Great Wall, shows that the universe is rich in variety and scale. Compared to Sloane's Great Wall, the Giant Arc and the Great Ring are more unique formations. The wall is a branded chain of galaxies, while the arc and the ring have a more distinct shape, suggesting that their creation was influenced by very different cosmic processes. As we delve into the mysteries of their origin, we explore various theories and models. Among the hypothesized mechanisms of their formation is the influence of dark matter, an invisible but pervasive component of the cosmos. Its gravitational attraction could organize the clustering of galaxies into these huge arrangements. The cosmic web theory proposes a universe in which galaxies are interconnected by threads of denser matter. These megastructures may represent intersections or particularly dense regions of this cosmic web. Another interesting theory is the theory of baryon acoustic oscillations, commonly known as BAO. These cosmic echoes are not just remnants of the early universe, but potential clues to unraveling the mysteries of structures such as the Giant Arc and the Great Ring. SAOs are thought to have originated in the early universe during a period of intense heat and density. Here, baryons, particles such as protons and neutrons, were in constant interaction with photons, particles of light. This interaction created pressure waves, similar to sound waves, rolling through the hot plasma of the early universe. Imagine a stone thrown into a quiet pond. The impact creates ripples that spread out in concentric circles. In the same way, SAW spread through the early universe, creating ripples in the very fabric of space. These ripples or acoustic waves left their mark on the distribution of matter in the universe. As the universe expanded and cooled, these acoustic waves froze in place, imprinting a unique pattern into the cosmic microwave background, the afterglow of the Big Bang. This pattern extends to the distribution of galaxies and cosmic structures, influencing their formation and location. The BAO imprint is not just a relic of the past, but a tool for astronomers. By studying these patterns, scientists can trace the expansion of the universe and the formation of structures like the Giant Arc and the Great Ring. BAO helps us understand the scale of these structures and provides clues about the nature of dark matter and dark energy. However, there are alternative theories. These are Roger Penrose's conformal cyclic cosmology and the cosmic string hypothesis, each of which offers a unique angle on the fabric of the cosmos. Roger Penrose, a famous physicist, proposes a fundamentally different idea in his conformal cyclic cosmology. According to this theory, the universe goes through a series of cycles, each beginning with the Big Bang and ending in a smooth, infinite expansion. From this point of view, our present-day universe is just one phase in an eternal sequence of cosmic events. Penrose's theory challenges the traditional view of a single Big Bang. Instead, he argues that the end of each universe becomes the conformally scaled beginning of the next. This cycle of death and rebirth, devoid of singularities, provides a thought-provoking alternative to our understanding of time and space. Now, how does this relate to our megastructures? This can be directly understood through several key aspects of the theory. In CCC, the final state of the previous universe cycle, which is infinitely extended and empty of matter, can influence the beginning of the next cycle. This influence is exercised not through matter as it is dispersed, but through the conformal geometry of space-time. In essence, the geometry of the previous universe imposes itself on the next. Penrose suggests that certain characteristics of the universe, especially its geometry, may be transferred through these cycles. This transfer has the potential to imprint large-scale structures from one cycle to the next. When a new universe cycle, a new Big Bang begins, these imprints or remnants of the previous universe may manifest themselves as initial conditions or irregularities in the cosmic microwave background. These irregularities, in turn, may have affected the distribution of matter in the early universe, leading to the formation of massive structures such as the giant arc. This challenges the standard cosmological principle of uniformity, suggesting that the large-scale structure of the universe may not be completely random, but rather influenced by the echoes of past cycles. While conventional cosmology attempts to explain the existence of such huge structures within the age of the observable universe, CCC proposes an alternative path. It suggests that these structures may not be anomalies, but rather features influenced by the cyclic nature of the universe. Another exciting concept is that of cosmic strings. These hypothetical one-dimensional defects in space-time may have formed in the universe's early moments. Resembling cracks or lines of immense gravitational attraction, cosmic strings, as scientists believe, may have a profound effect on the surrounding space. According to the hypothesis, these strings may act as cosmic-scale stitching, affecting the distribution of galaxies and possibly causing the unusual alignments observed in structures such as the Great Arc and the Great Ring. Their existence, while still theoretical, opens a fascinating window into the complexity of the early universe. The quest to prove or disprove these ideas drives our scientific research forward, lighting the way to the deeper truths of cosmology. Our understanding of the evolution of the universe is constantly changing thanks to these discoveries. These colossal formations, such as the Giant Arc and the Great Ring, they force us to reconsider the fundamental processes governing the evolution of the universe and current cosmological models. Think about the impact of these giant structures on cosmic evolution. They're not just clusters of galaxies. They're vast networks of matter and energy that affect the gravitational balance of the cosmos. Their existence suggests that the universe may be connected far more tightly than we ever imagined. These discoveries emphasize the interconnectedness of various cosmic phenomena. From the birth of stars to the mysterious nature of dark matter, everything in the universe is part of a grand interwoven plan. The large-scale structures we observe may be important for understanding how the various forces and components of the universe interact over astronomical distances and timescales. As our technological capabilities grow, so does our potential for astronomical breakthroughs. The future of space exploration and observation holds untold possibilities. With each new discovery, we peel away another layer of the universe's mysteries, moving closer to understanding the grand design of this vast cosmic sea. In the meantime, we look forward to new discoveries that will shed more light on the megastructures of our universe.